So in today's video, I'm going to be talking about some pretty interesting results and applications of dynamics and Lagrangians and variational principles. We're going to be able to show that if you want to parameterize a specific curve, we can do so in a totally different field. Like from outside of math, we can use physical dynamics, basically physics, but physics and math, but basically application of physics of math to show how you can get. So there's a correspondence between a physical way to describe a particle and then the equation of motion will relate to a mathematical description we didn't even have to discover. We could have just wrote down what the curve is for like a circle, like, you know, it's like sine theta times r, and then the other one's r cosine theta, and that's, you parameterize it in terms of theta and let theta be like function of time, so it goes on like spin around. So we're going to be dealing with particularly free particles and constraints that don't depend on time. So it's going to be scleronomic. And I'm basically taking information from Goldstein, whatever, Chapter 2, 3rd edition. And okay, so here's some stuff we're going to need. Imagine we had a Lagrangian free particle. So it's a function of just q dots. And it's free. I'm going to say it doesn't depend on time either. It's free particle. Just kinetic energy. Okay, and then imagine we have some constraints that are also just going to be functions of just q. I shouldn't put the I. The bar up top means q1, q2, q3, like a vector. And it could be, we're not going to deal with them, but they could be functions of velocity too. And of time. We're only dealing with specific cases of particles on curves, and we're going to show that a particle on a curve, the dynamics of it, the equation of motion, corresponds to just writing the parameterized curve. But it's going to have physical quantities in there. Okay, so this is going to be equal to 0. And we can have an alpha number of constraints. Alright. So you get something pretty cool if you define your modified Lagrangian L star. It's going to be equal to L plus the sum from J1 to alpha. These lambdas, we're adding them in. They're new coordinates we don't know. Or we're going to treat them like new coordinates. And there's going to be J of them. I mean alpha of them, but it's J index. And this is going to be our constraint. I don't have to write it, but I did. And the same thing here. Q dots. 1, 2, 3, whatever. Doesn't matter how many. But now we're gonna treat this Lagrangian like well, it could be alpha. Let me put a bar to correspond. It could be alpha of this, so there's 1, 2, 3, alpha. Okay. So now from Goldstein, it basically the result is you get the Euler-Lagrange equations of this result in you could just treat this like Euler-Lagrange, where you treat the number of variables plus alpha new variables or coordinates. Treat them the same way. You get equations of motion. So you get how many, like n of these plus alpha, so you get n plus alpha equations, and then you solve them. And basically, get the equations in motion. Okay. I could show you what they're going to be, I guess. So if you just do the Euler-Lagrange, it results in, well, for the alphas, basically just, if you solve it for the Euler-Lagrange, let's call it alpha j's now. The j represents each one of these. Same thing though. And alpha j dot equal to 0. And then the other ones, when you do it for the q's coordinates, well, let me write this gives you basically just alpha equal to 0. So for each, well, this is the general version. This stands for just one of them. I should write j there. For the j, it gives you, for each j, it basically just returns you the same, constraint, Scleronomic constraint. But when you do the other ones, for the QIs, do the same Euler-Lagrange, but with modified. And you, this is the same as the old Euler-Lagrange. But, and because, I can write it out. There's two other terms in here in the sum. Because you see when you take respect to q, it's going to be in here. So you get a sum. But because I didn't write it up there explicitly, there should be a, when you take the partial, this depends on time. And this could also depend on, it doesn't though, because I wrote it explicitly. In that chapter, it gives you a longer expression with 3 extra terms that depend on time. Derivative of the coordinates of q dots. There's no q dots though. If there was a q dot, you'd have 2 other terms. That's all I'm trying to say. You end up getting a sum. You can even see it real quick. You just do, you keep everything the same. Oh. That's minus. Because it's when it's on this side, subtract it over. And it becomes f partial qi. And j is going to go from 1 to alpha. Alpha is the number of constraints. I think that's why I wrote it up there. Well, number of Scleronomic constraints of this one. Okay, so you basically are gonna write your equations down as much as you can, and then plug in what these constraints are into here. So what you're gonna do is try to solve for this as far as you can, and then you're gonna plug this into there. It's like treating your dynamical system or in like a fancier way, like more complex, and then you get to keep along the way extra things that tell you a lot about the system. Because usually when you do Lagrange, you don't get to keep like forces, as in the Newtonian you can if you do Newton's F equals ma. This turns out this term is it's the negative is the same, but this term right here is the ith generalized force. And ith corresponds to the coordinate. The j, double checking, don't get lost. J stands for the constraint. So for each coordinate, there's a sum here, because it could be all the constraints you're worrying about, and each f also depends on all the coordinates. That's what this bar means. Okay, so just to put that in perspective, now we can write down explicitly this and what this is, because it's just going to be kinetic energy. And then what we're going to do is do this as far as we can and then plug in our constraint. And then we're going to note, just for funsies, because it's physics, we're going to talk about this, if it makes sense, what's going on with that, and then we're going to correspond that to the math way. Like, what does it mean? Like, I could have just wrote this constraint without even, like, I could write the like a parametric curve. I can't say that word. Parametric curve of a circle or a straight line without doing any of this. But this is just cool how you can use it. Okay. Okay. So free particle. So we're going to correspond to free particle, like I said. So that means our Lagrangian is just kinetic energy, which is m/2, our coordinates, and the first one we're going to do a straight line to the origin. So we're going to talk about the dynamics of a straight line that has to stay on the curve that passes through the origin. So the line is y equals x. So our constraint that we're going to define for this is F1, only one constraint. I only want a free particle that has to travel along this curve. And it's of x and y, no derivatives of x or y. And you could say y minus x or x minus y. Doesn't matter. And free particle, only kinetic energy term is that. We set it up and we write down our modified Lagrangian. Oh, we don't have to do that, but because I wrote down what the result is. But in perspective, you could write L star is equal to L plus only one constraint. It's a sum, but only one constraint here, one equation. Y minus x. Like I said, we treat this like it's a normal Lagrangian with one more term, so it's 1, 2, 3 variables. And the third variable, we can already write it down because we know it just gives you this, so we get y is equal to x. That's one of the Lagrange equations for this. X variable, what do we get? We get, we do the normal Lagrange, we basically treat it like a normal Lagrangian, and then the left side, generalized force. And there's only one term, not a sum anymore. You get is equal to, it was negative this f1, and then it's the partial of f1 with respect to x. And what do you get? That is -1, and -1 times -1 is 1, so you get is equal to that. And for y, you're going to get the opposite. -1 times 1 is equal to -λ1. So, like I said earlier, we want to try to go as far as we can with this and then use the constraint. So, these two, what do they give you? You try to solve for lambdas and then plug in the other one to the other one. It doesn't matter which way. you're gonna get to the same conclusion. So what I say, m is equal to lambda 1. So then we plug it into the second equation, we get m. M's go away. I can say that out loud. Y dot is equal to negative lambda, but we said lambda is that, and m's. And here comes this is as far as we can go without saying what lambda is. We eliminated it. Lambda 1. We know that must be true, and we don't want to work with the trivial solution where there is no dynamics. You could say where x and y just stay at the origin. It would work, but it would be trivial. So with this in mind, this implies that they have to be equal to 0, which implies that lambda, it doesn't imply lambda. This implies that these both have to be equal to 0. And we're claiming, I don't want it to be trivial, so we don't want the velocities. We don't want the velocities to be 0, right? So we know the velocities can't be 0. I mean, they must be equal, but opposite. And then we're going to look here and we say, oh, but y must be equal to x. That's the other constraint we get. The first constraint, when we treat the lambda 1 as coordinate. We say, whoa, well, the only thing that can make this work is if these are both equal to the same thing, which is 0. That doesn't imply this is 0, because when you take a integral of that, you get a constant. And take another integral, and you get a constant times t. So we end up getting, and they both are the same constant. And because of this, the constants have to be the same. So this is going to imply that y and x are equal to some constant times time. I called it c. And it's the same constant. Because this also, if it wasn't the same constant, this wouldn't hold. Y equals x. So the cool thing I wanted to note also, we could also note as, well, first, equations of motion are a straight line that pass through the origin. And then the generalized force is basically this term is like F equal ma. So you get in the x direction along this curve, at any point, the particle is going to experience a force pushing it that way. And there's going to be another force pushing it down, which doesn't look like it makes sense, but that's what happens. So as it moves, since this constant can be negative or positive, as it moves, it's going to experience a force to keep it on the line, basically. So for the qx and the qy, or I would rather say that's not the, that's more of a magnitude, because as it moves up or down, well, if it moves up, if it moves up, it's going to experience a force this way and this way. So it'll keep it on this line going up. And the same goes for, if it was going this way, there'd be a force going that way and a force going down. So the magnitude of the forces is lambda 1. And we know, Oh, time out. I just had a revelation. This is why I make these videos. Because this is equal to 0, we know lambda 1 is equal to 0. So the generalized force in both directions are 0. It makes sense physically because if you're on a plane and you're just moving out in a straight line, there will be no force in you. I was being dumb there. So physically, the dynamics of a free particle constrained to move on a straight line through the origin makes sense. The forces acting on is 0 in both x and y coordinate directions. And this is a function of time. It's dynamics. I'll write it explicitly. As time increases, it goes up. Both directions. Time can be negative. It doesn't matter. Or we can just make the constant negative. Whatever our initial conditions were for the constant. And as I was trying to note earlier, we could have simply just wrote down a parametric equation to describe this line in terms of x and y. So I could have just wrote x of t is equal to, let's call it at, and y of t. So this is physics. This is pure math view of this line. We could have said at, and this gives you this line. This will give you the constraint. So I find it interesting that these imply basically the same thing. So if we approach a problem in physics with the constraint, it's identical to just declaring this pure math view. But the only difference is we can talk about generalized forces, and this constant here will depend on physical quantities. This one, it doesn't matter. But here, as you see in the circle, when I do a circle, it will depend on physical quantities, and it'll be neater than this example. So I'll do that real quick. So, free particle again, but since it's a circle, you probably know I'm going to be using polar coordinates. And then you probably know this by heart too. That's what it is in polar coordinates. And in polar coordinates, I'm going to be using the constraint r minus 1 is equal to 0. And you're going to see this function is only a function of r now. There's no theta. Okay? Yeah, I think that's it. And then you'll see if we do the same steps, we get r is equal to 1. If you do the modified Lagrangian, we do the thing like I said in the very beginning, and then here comes the fun part. Where is it? So what do we get? Well, let's do the Q's. QR. QR is just derivative of f with respect to r, which is 1. So it's lambda. It's lambda 1 times 1. And then Q theta is 0 because it doesn't depend on doesn't depend on theta. Just take derivative of the coordinate theta. It's gonna be 0. And then what is the Euler Lagrange? I wrote it here earlier, but this is the same thing. Well, with respect to R, you get m r theta dot squared minus m r dot is equal to negative lambda 1. And in this one, same thing. What do you get? So this is going to be a cyclic coordinate one, where you've probably done this one a billion times too. It's a cyclic one, and then you're going to use, you basically get, this is 0, so that's 0. So you get dt of dl dot, which is just mr squared theta dot. This implies, call a constant L. Is equal to L. Okay? This constant usually is angular momentum when you talk about it physically. So we have 3 guys on our hands. We have that guy, this guy, and we also got the generalized forces in their direction. Okay. So what are these guys? Let's find the equation of motion. Okay, so I could plug in, I could plug in theta dot here, and then solve for R. When you do that, that's as far as you can go, and then I think you're going to have to use R equals 1. And if that's the case, I believe we can just plug it in right away. So you basically just get, if we use R equals 1, m theta dot squared minus m r dot dot is 0 because R is equal to 1 is equal to negative lambda. And then we also get m times 1 times theta dot is equal to L. So we have 2 equations and 2 unknowns. We know is equal to L over M because of this guy. And this guy gives we could plug this quantity up there, and we get L M times M squared is equal to negative 1. So squared goes away, so I get L squared negative over M is equal to lambda 1. So we have everything we need now for the equation of motion. R of t is 1. Theta of t. We do a time derivative, so integrate it once. Depends on our initial condition. We can say it started here at theta equals 0. So we get L over mt plus 0. Okay. And we end up getting this generalized force is 0. Makes sense. And then QR is equal to negative, that's right, yeah, L squared over M. So that is our dynamics view, okay? And it makes sense when it's a particle is constrained to move on a circle, the only thing acting on it is a force in the R direction, negative. That's so cool. And then, yeah, this is the R direction is, you know how it works. And then theta is going to be perpendicular, and it doesn't make sense to have any force in the theta direction. And what's cool is, I think it's angular momentum over m squared, I believe. It may be in it may be in right dimensions of a force, but it's a generalized force, so it could be something weird. But besides that, this is similar if I just wrote R equals 1, theta is a function of time, some constant, I don't know, we call it AT, and that's all you would have. So this is physics. This is the pure math view. So once again, we used a pretty advanced overkill method of a free particle with a constraint. And then we showed that the physics dynamical view is identical or corresponds to parameterizing a curve of the constraint we're talking about. And we see this A doesn't have any physical meaning. Here it does, angular momentum over mass. And this one, we also get the generalized force that has also physical meaning. Yeah, but we could have just wrote this down of the particle, like, oh, of course it's gonna, that's what's gonna be, it's gonna stay at the same radius of 1, and then it's gonna move around the circle, like I guess linearly. But I find this interesting, and this topic is pretty cool. You could also do this for, I'm not gonna write it down, for ellipses and parabolas. I believe this could be done for any closed curve or open. So it would be cool and interesting to know, does this method work of the dynamical physics variational approach of a problem on a free particle to the pure mathematical view of it? Can it work for like any plane curve? Also, would this be possible in other coordinate spaces of different variational, like if the physics wasn't classical physics, what if it was special relativity, or a different, like the Lagrange would be different, and then so would the same principles be the same, but the Lagrange would be different. And I think the principles would be similar concept but different approach. But any plane curve does this work, like ellipse or any function I give you. It would in crazy curves that aren't simple like this or a straight line. The generalized forces would be very interesting to look at too, because it wouldn't be as simple as a constant force as it goes around the circle. Or a straight line, zero force is found. And that's it. This is an interesting topic and idea and approach to solving some problems. Alright, bye.